This conference will now be recorded.
Good morning, all. We will start with our session. Can anyone confirm if I'm audible and is my voice clear? Can anyone confirm if I'm audible and is my voice clear? Am I audible? Can anyone confirm if I'm audible and is my voice clear?
Yes, you are audible.
Okay. So today we are going to give a demo on design for testability, which is DFT. So before we go into what is DFT, we'll try to understand what is VLSI. So VLSI stands for very large scale integration. So VLSI stands for very large scale integration. Large scale integration. So VLSI stands for very large scale integration. Okay. So it means implementation of million transistors in a small area. Goal of VLSI. So if a particular company is designing a chip, then they will be having some primary conditions or primary goals to be met. So that is what is the goal of VLSI. So one is high performance. High performance ensuring faster processing. So high performance ensuring faster processing. And then we have low power. So optimizing the power usage to extend the battery life. So optimizing the power to extend the battery life, okay. And then low area. So low area, it is actually reducing the chip size to achieve compact products. Low area is to reduce the chip size, reducing the chip size to achieve compact products, Okay, so that is what is low area. So reducing the chip size to achieve compact products. So this is how our chip will look like. Okay, so as seen in the picture, this is how our chip will look like. And in the next slide, we'll try to discuss about ASIC flow. ASIC stands for Application Specific Integrated Circuit. ASIC stands for Application Specific Integrated Circuit. So application specific integrated circuit, it means it is an IC that's custom designed for a particular application. So it is an IC that's custom designed for a particular application. That's custom designed for a particular application. So that is what is ASIC. Okay. So ASIC stands for Application Specific Integrated Circuit. Application Specific Integrated Circuit. So it is actually an IC that's custom designed for a particular application. It is an IC that's custom designed for a particular application. Okay. So let me just give you an idea, like an example. Let me just try to explain what is ASIC with the help of an example. Okay. So say for example, so application specific integrated circuit means it is an IC that's custom designed for a particular application. So say for example, a modem chip can't be used as a chip which is used for deployment of airbag in automotive. A modem chip It can't be used. Can't be used as a chip, which is used for deployment of airbag in automobile. Deployment of airbag in automobile. In automobile. Okay. So that is what is ASIC. So ASIC means application specific integrated circuit. So it's an IC that's custom designed for a particular application. So which means a modern chip, it can't be used as a chip which is used for deployment of airbag in automobile. So ASIC flow means it actually gives the steps which we need to follow for designing a chip. So which means it actually gives the various steps which is involved in the process of chip design. So ASIC flow, it gives the steps which we need to follow for designing a chip. So it basically gives you the steps which is involved in the process of chip design. Okay. So the first step will be the design specification stage. So in the design specification stage, what will happen is, based on the application for which we are designing the chip, certain specifications like how many memory modules, processors, sensors are required, what has to be the power. So such kind of specifications will be decided during the design specification stage. Okay. So based on the application for which we are designing the chip. So based on the application for which we are designing the chip. For which we are designing the chip. We are designing the chip. Designing the chip. Certain specifications. Okay. Certain specifications. Like how many memory modules. Okay. How many memory modules, and then processors, okay, and then sensors are required. Okay, and then what has to be the power. So what has to be the power? Okay, so etc. So these kind of specifications will be decided. During the design specification stage. So during the design specification stage, based on the application for which we are designing the chip, certain specifications like how many memory modules, processors, sensors are required, what has to be the power. So such kind of specifications will be decided during the design specification stage. Okay, so based on the application for which we are designing the chip, certain specifications like how many memory modules, processors, sensors are required, what has to be the power. So such kind of specifications will be decided during the design specification stage. Now after the design specification stage, we will be having the design code stage. So design code stage, what will happen is the design team, they will be writing the design code of the chip. So design team will write the design code of the chip. Okay. So design team, they will write the design code of the chip. Okay. So they are basically describing the functionality of the chip. They are describing the functionality of the chip. Okay. So design team, they will write in behavioral model and data flow level model. Okay. So design team will write in behavioral model and data flow level model. Will write in behavioral model and data flow level model. Okay. So design team, they will write the design code of the chip. They are describing the functionality of the chip. So design team will write in behavioral model and data flow level Okay, so design code, next stage was a design code stage. So design team, they will write the design code of the chip. They are describing the functionality of the chip. So design team, they will write in behavioral model and data flow level model. Now after this, we have the verification. Verification is actually to validate the functionality of the design to ensure that it meets the required specification and performs as intended. Okay, so verification, it is actually to validate the functionality of the design. Okay, it is used to validate the functionality of the design. Validate the functionality of the design. Functionality of the design to ensure that it meets the required specification and performs as intended. Okay, it meets the required specification and performs as intended. Okay, so this is one. So verification, it is used to validate the functionality of the design to ensure that it meets the required specification and performs as intended. So this is what is the verification stage. Okay, so it is actually used to validate the functionality of the design. It is to validate the functionality of the design to ensure that it meets the required specification and performs as intended. So what will happen during the verification stage? Okay, it is to validate the functionality of the design to ensure that it meets the required specification and performs as intended. And after this, we have the synthesis stage. So during the synthesis stage, what will happen is the behavioral and data flow level model code, it will get converted into a structural form, or we can call it as a technology node specific gate level netlist. Okay, so this behavioral model and data flow level model, this behavioral model and data flow level model code was there, right? That will get converted into a structural form, or we can call it as a technology node specific gate level netlist. Okay, so the behavioral model and data flow level model code. Data flow level model code, what will happen? It will get converted into a structural form. It will get converted into a structural form. We can even call it as a technology node specific gate level netlist. It will get converted into a technology node specific gate level netlist. Technology node specific gate level netlist. Okay, so the behavioral model and data flow level model, that code, it will get converted into a structural form, or we can call it as a technology node specific gate level netlist. Okay, and then after synthesis, we have the design for testability team. We will discuss about design for testability more in detail in the upcoming slides. We will discuss about this design for testability more in detail in the upcoming slides. Okay. Next, after the design for testability team, we have the physical design team. So physical design team, what do? Is they actually convert the gate level netlist into layout form. Okay, physical design team, they will be converting the gate level netlist into layout form. So the gate level netlist is converted into layout form. Is converted into a layout form. Okay, so this is what. So what will happen? Physical design team, what do? The gate level netlist is converted into a layout form. Okay, so physical design team, what do? They convert the gate level netlist. The gate level netlist is converted into a layout form. And after that, we have sign off. So in sign off, we are going to perform 3 things. So one is STA, then we have physical verification PV, and then logical equivalence check LEC. Okay, so we will be having STA and then physical verification PV and logical equivalence check LEC. So what is it? Let's try to understand. So let me just explain each of the steps. So STA. So STA, it stands for static timing analysis. So the full form of STA is static timing analysis. So this is what is the full form of STA. Static timing analysis. This is the full form of STA. Static timing analysis. Okay. So this is what is the full form of STA. Static timing analysis. So what is it? Static timing analysis. So it is a method of validating the timing performance of a design. So it is a method of validating the timing performance of the design. Validating the timing performance of the design. Timing performance of a design. Timing performance of a design. Okay. By checking all possible paths for timing violations. By checking all possible paths for timing violation. All possible paths for timing violations. For timing violations. Okay. So STA is nothing but static timing analysis. So it is a method of validating the timing performance of the design. Okay. It is actually a method of validating the timing performance of the design. Okay. By checking all possible paths for timing violation. By checking all possible paths for timing violations. So STA stands for static timing analysis. So it is a method of validating the timing performance of a design by checking all possible paths for timing violations. And then we have physical verification, PV. PV is nothing but physical verification. Physical verification, PV. So physical verification. Physical verification, it is actually to Physical verification, it is actually to verify the layout of the circuits. So physical verification, it is actually to verify the layout of the circuits. It is actually to verify the layout of the circuits. Layout of the circuits. Okay. And then we have the logical equivalence check, LEC. LEC stands for logical equivalence check. Logical equivalence check. Equivalence checks. So LEC stands for logical equivalence checks. So why is this LEC required? Why is this LEC required? So if you see, our design undergoes a lot of changes in each stage. Okay, our design undergoes a lot of changes in each stage. Undergoes a lot of changes in each stage. In each stage. Okay, our design, it undergoes a lot of changes in each stage. So say for example, first we had the behavioral and data flow level model code. Okay, so first we had the behavioral model and data flow level model code. Behavioral model and data flow level model. Data flow level model. Okay, so first we had the behavioral model and data flow level model code. So this behavioral model and data flow level model code, it had got converted into a technology node specific gate level netlist. It had got converted into a technology node specific gate level netlist. Technology node specific gate level netlist. Gate level netlist. Okay, the behavioral and data flow level model code, it got converted into a technology node specific gate level netlist. And then certain special cells for low power design. If you are going for low power design, then certain special cells for low power design like isolation cells, clock gators, all those things have to be added. Okay, so certain special cells for low power design. special cells for low power design. Low power design. Low power design like isolation cells, clock gators, all these things will be added. Okay, so we first had the behavioral and data flow level model code. So that got converted into a technology node specific gate level netlist. And if in case we are going for low power design, then certain special cells for low power design like isolation cells, clock gators, all those things also will be added. And DFT test structures, we will be adding our own DFT test structures. We will be adding that, we'll be discussing in the upcoming slides. So we'll be adding our own DFT test structures. We will be adding it. So DFT test structures will be added. DFT test structures will be added. Okay, so DFT test structures will be added. So if you see, our design undergoes a lot of changes in each stage. Okay, so first we had the behavioral and data flow level model code. So that got converted into a technology node specific gate level netlist. And certain special cells for low power design like isolation cells, clock gators. So all those things also will be included into your design. Okay. And then like we will be adding DFT team will be adding their own test structures, which we will see an idea in the upcoming slides. So DFT test structures will also be added. So if you see, our design undergoes a lot of changes in each stage. Okay, so that is why LEC is actually done to check whether the final design is logically equivalent to the original design or not. Okay, so therefore LEC is done. LEC is done. Okay, to check whether the final design, whether the final design is logically equivalent to the original design. Is logically equivalent to the original design. Okay. So LEC is actually performed after each stage, like after synthesis, after DFT insertions, after PD, like that. Okay, so LEC is actually performed after each stage. LEC is performed after each stage. Okay, like after synthesis, and then after DFT insertions, after PD, like, okay. So LEC stands for logical equivalence check. So our design undergoes a lot of changes in each stage. As you can see, we had seen in the previous slide, right? So first we had the behavioral model and data flow level model. So that got converted into a technology node specific gate level netlist. And if you're going for low power design, then certain special cells for low power design like isolation cells, clock gators, those things will be added. And then DFT test structures will also be added. DFT team will be adding our own test structures. So if you see, our design undergoes a lot of changes in each stage. So that's why LEC is done to check whether the final design is logically equivalent to the original design. So LEC will be performed after each stage, like after synthesis, after DFT insertion, after PD, like that LEC will be performed after each stage. Okay. So these are the three things which we have seen. We have seen about the STA, and then we have discussed about this STA and physical verification PV and logical equivalence check LEC. So STA is nothing but static timing analysis, PV is nothing but physical verification, and LEC is nothing but logical equivalence check. Okay. And after this, we have tape out. So tape out means delivering the database to the manufacturing unit. So that is what is called as tape out. Tape out means delivering the database to the manufacturing unit. So that is what is tape out. Delivering the database to the manufacturing unit. So that is what is called as tape out. So tape out means delivering the database to the manufacturing unit. And then you'll be having this packaging and testing. So this packaging and testing, it is actually done after manufacturing. Packaging and testing, it is done after manufacturing. Okay. So packaging. Packaging means covering the die with a protective layer is called as packaging. So you have like this. So this complete circle will be a wafer and each small portion in it is called as a die. So packaging means covering this die with a protective layer is called as packaging. Okay, so packaging means covering the die with a protective layer. Packaging means covering the die with a protective layer. Covering the die with a protective layer. With a protective layer. Protective layer. So that is what is called as packaging. So covering the die with a protective layer is called as packaging. And then testing. So testing, it is actually done to check whether our chip is good or not. That is to check whether there are any manufacturing defects or not. So after this, you have this testing, right? So this testing, it is actually done to check whether our chip is good or not. Okay, so this testing, it is actually to check if our chip is good or not. If our chip is good or not. Good or not. Okay. So that is to check whether there are any manufacturing defects or not. That is to check whether there are any manufacturing defects or not. Okay, testing is actually done to check whether our chip is good or not. That is to check whether there are any manufacturing defects or not. That is to check whether there are any manufacturing defects or not. Whether there are any manufacturing defects or not. Manufacturing defects or okay, so testing, it is actually to check if our chip is good or not. That is to check whether there are any manufacturing defects or not. Okay, so this is what is the ASIC flow. So this complete slide is nothing but the ASIC flow. So it actually gives the various steps which is involved in the process of chip design. These are the various steps which is involved in the chip design process. So now we have tried to understand about the complete ASIC flow. We have tried to understand the complete ASIC flow. We have got an idea on what is this complete ASIC flow. The various steps which is involved in ASIC flow, we have tried to understand. Okay. So in the upcoming slides, we will try to discuss more in detail about what is this verification. Okay. And then what is DFT, and also regarding this testing. So all these things we will discuss in detail in the upcoming slides. We will discuss in detail during the upcoming slides. So in the upcoming slides, we'll try to discuss what is verification, what is like more in detail. We'll try to understand what happens in this verification, what is designed for testability, and what is testing. We will try to understand in the upcoming slides more in detail. Okay. So what is DFT? DFT is actually to insert test structures in the design. Like we will be adding our own test structures in the design, like scan insertion. Okay, so scan insertion, and then MBIST insertion, boundary scan insertion. Like that, we will be adding our own test structures in the design. Okay. So DFT is to add test structures in the design. Like we will be adding our own test structures like scan insertion, MBIST insertion, boundary scan insertion. Like that, we will be adding our own test structures in the design during the pre-silicon stage to facilitate detection of manufacturing defects in the chip. To facilitate means to help detection of manufacturing defects in the chip. To help detection of manufacturing defects in the chip. So DFT is to insert test structures in the design. So DFT, we will be adding our own test structures in the design like scan insertion, MBIST insertion, boundary scan insertion. Like that, we will be adding our own test structures in the design during the pre-silicon stage. Pre-silicon stage means before manufacturing. Pre-silicon stage means before manufacturing. To facilitate, that is to help detection of manufacturing defects in the chip. Okay, so DFT is to insert test structures in the design during the pre-silicon stage. Pre-silicon stage means before manufacturing, to facilitate, to help detection of manufacturing defects in the chip. So we will be adding our own test structures in the design, like scan insertion, MBIST insertion, boundary scan insertion, like that. We'll be adding our own test structures in the design during the pre-silicon stage. Pre-silicon stage means before manufacturing. Okay, to facilitate, that is to help detection of manufacturing defects in the chip. So which means if suppose a particular chip fails after manufacturing. Okay, so if suppose a particular chip fails after manufacturing, a particular chip fails after manufacturing. Okay, so suppose a particular chip fails after manufacturing, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. What manufacturing defect has caused the chip to fail. Okay. So DFT is to insert test structures in the design. Like we'll be adding our own test structures like scan insertion, MBIST insertion, boundary scan insertion during the pre-silicon stage. So pre-silicon stage means before manufacturing. To facilitate, that is to help detection of manufacturing defects in the chip. So if suppose a particular chip fails after manufacturing, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. Okay. And then role of DFT engineer. Role of DFT engineer. So DFT is to insert test structures in the design during the pre-silicon stage to facilitate detection of manufacturing defects in the chip. So DFT is to insert test structures in the design during the pre-silicon stage to facilitate detection of manufacturing defects in the chip. So yes, that is what we had discussed it in the previous slide. So DFT engineers do not check the functionality of the chip. Okay, DFT engineers do not check the functionality of the chip. They rather check the quality of the chip. So DFT engineers do not check the functionality of the chip. We rather check the quality of the chip. So what does that mean? Let's try to understand here. So DFT engineers do not check the functionality of the chip. We rather check the quality of the chip. So what does that mean? Let's try to understand with the help of this slide. So consider a half-added design. So half-added design, as you will be knowing, sum is nothing but A XOR B, carry will be A. Whether this is correct or not, so this will be checked by the functional verification team. So whether this is correct or not, so this one will be checked by the functional verification team. So functional verification team, they will be checking the functionality. Functional verification team, they will be checking the functionality. Okay, so for this one, suppose if half added is nothing but sum is equal to A XOR B, carry is equal to AB. So whether that is correct or not, that is what will be checked by the functional verification team. They will be checking the functionality. So by mistake, if someone has written sum is equal to A plus B, carry is equal to A. Okay, by mistake, if someone has written sum is equal to A plus B, carry is equal to AB, this will not function like a half adder. This will not function like a half adder. So by mistake, if someone has written sum is equal to A plus B, carry is equal to AB, this will not function like a half adder. So this is what will be checked by the functional verification team. They will be checking the functionality. Okay, this is what will be checked by the functional verification team. They will be checking the functionality. Now, DFT team, we do not check the functionality. DFT team, we do not check the functionality. We check whether each and every net of the half added is free of defects or not. We check whether each and every net of the half adder is free of defects or not. So this is what is our intended design. This is what is our intended design. Okay. So like here, if you see, we are having this XOR gate. So sum is A XOR B. A and B both are XOR is sum. A and B both are ANDed is carry. So A and B, it is coming from some flops, and sum and carry, it is going back again to a flop. So this is what is the intended design. Now suppose during manufacturing, unintentionally during manufacturing, A net of this AND gate has got connected to ground. So unintentionally during manufacturing, A net of this AND gate has got connected to ground like this. Okay, so unintentionally during manufacturing, A net of this AND gate has got connected to ground like this. So this is what will be checked by the DFT key. We do not check the functionality. We check whether each and every net of the half adder is free of defects or not. So this is what is our intended design. So sum is A XOR B, carry is AB. This is what is our intended design. So A and B, it is coming from some flops, and then sum and carry, it is going back again to some flops. Now suppose during manufacturing, what has happened? Unintentionally during manufacturing, A net of this AND gate has got connected to ground. Okay, unintentionally during manufacturing, A net of this AND gate has got connected to ground. So this is what will be checked by the DFT team. We do not check the functionality, we check whether each and every net of the half adder is free of defects or not. So unintentionally during manufacturing, A net of this AND gate has got connected to ground. So this is what will be checked by the DFT team. We do not check the functionality, we check whether each and every net of the half adder is free of defects or not. Okay. So now let's try to strengthen our understanding. Let's try to understand more in detail. Like, why do we need a functional verification team? So why do we need a functional verification team and DFT team? So in the ASIC flow slide, we have discussed it, right? So we have both the teams, verification as well as a DFT team. So we'll strengthen our understanding with the help of another example by taking up another example. Like, why do we need a functional verification team as well as a DFT team? Okay, we will strengthen our understanding on why do we need a functional verification team as well as a DFT team. Okay, so we'll take up another example in order to strengthen our understanding on why do we need a functional verification team and a DFT team. Okay, so first let us try to understand why do we need a DFT team? Why do we need a DFT team when we have functional verification team? Okay, why do we need a DFT team when we have a functional verification team? So consider our design. So our design, it is actually a 10-bit counter with a counter initialization and a counter observation circuit. Okay, so you are having a 10-bit counter with a counter initialization and a counter observation circuit. So suppose the counter is manufactured with a defect. So suppose the counter is manufactured with a defect. So consider that after counting 999, instead of counting 1000, it incorrectly rolls back to 999. Okay, so consider that in a design, you're having a 10-bit counter with a counter initialization and a counter observation circuit. Scenario is, suppose the counter is manufactured with a defect. So that's why after counting 999, instead of counting 1000, it incorrectly rolls back to 999. Okay, so scenario is you're having a 10-bit counter with a counter initialization and a counter observation circuit. Okay, that is what is your design. Scenario is suppose the counter is manufactured with a defect. So that's why after counting 999, instead of counting 1000, it incorrectly rolls back to 999. Okay, so after counting 999, instead of counting 1000, it incorrectly rolls back to 999. Okay, so in this particular case, we will try to understand what will happen. What will happen if only functional verification tool exists, and what will happen if a DFT tool exists. So in this particular situation, we will try to understand what will happen if only functional verification tool exists and what will happen if a DFT tool exists. Okay, so first cases, only functional verification tool exists. Let's try to understand what will happen when only functional verification tool exists. So in our design, we are having a 10-bit counter with a counter initialization and counter observation circuit. The scenario which we are considering is suppose the counter is manufactured with a defect. So that's why after counting 999, instead of counting 1000, it incorrectly rolls back to 999. After counting 999, instead of counting 1000, it incorrectly rolls back to 999. Now we are considering what will happen if only functional verification team exists. So if only functional verification team exists, then what will happen? Functional team will test the counter using functional patterns. Functional team, they test the counter using functional patterns. So in this particular case, I'm saying that it will take more than 1000 clock pulses to tell that the counter is failing. In this particular case, I'm saying that it will take more than 1000 clock pulses to tell that the counter is failing. Can anyone just guess why will it take more than 1000 clock pulses to tell that the counter is failing in this particular case? 1 second, I think my screen sharing has stopped. Yeah, now it has stopped. Yeah. Can anyone just try to guess why will it take more than 1000 clock pulses to tell that the counter is failing in this particular case? Can you just read the scenario and try to guess from your side? Can anyone just try to guess? So here in this case, our design is a 10-bit counter with a counter initialization and an observation circuit. So scenario is the counter is manufactured with a defect. So that's why after counting 999, instead of counting 1000, it incorrectly rolls back to 999. Okay. So in this particular case, if only functional verification team is there, what will happen? Functional team, they test the counter using functional patterns. So I'm saying that it will take more than 1000 clock pulses to tell that the counter is failing. Can anyone say why? Why will it take more than 1000 clock pulses to tell that the counter is failing in this particular case? Okay, so let's try to see here. As we discussed in the previous slide, functional verification team, what do? They will be checking the functionality. Okay, functional verification team, what do? Functional verification team, they will check the functionality. Functional verification team, what do? They will be checking the functionality. Check the functionality. So which means they will check if the counter counts from 0 to 1023. That is, they will check if the counter counts from 0 to 1023. Counts from 0 to 1023. Okay, functional verification team check the functionality. That is, they will check if the counter counts from 0 to 1023. Okay, so here in this case, what is happening? Counter at which pulse it is failing. The counter is failing at dash pulse. So can anyone tell counter is failing at which pulse? Can anyone just see the situation and tell counter is manufactured with a defect? So that's why counter is counting 999 instead of counter is again counting 999 instead of counting 1000. Okay, so at which pulse is the counter failing in this case? Can anyone just guess at which pulse is the counter failing? So it has counted till 999. So after 999, instead of counting 1000, it is once again counting 999. So which means at which pulse is the counter failing? The counter is failing at the 1000th pulse. Okay, counter is failing at the 1000th pulse. At which count is the counter failing? So counter is failing at the 1000th pulse. Because at the 1000th pulse only, counter is again counting 999 instead of 1000. Okay, that is at the 1000th pulse. At the 1000th pulse, counter is again counting 999 instead of 1000. Counter is again counting 999. Again counting 999 instead of 1000. Instead of 1000. So counter is failing at the 1000th pulse because at the 1000th pulse, counter is again counting 999 instead of 1000. So that's why for this 1000 pulses are required. 1000 pulses are required. For this 1000 pulses are required. And then some more clock pulses will be required for counter initialization and counter observation. Some more clock pulses. Some more clock pulses are required for counter initialization and counter observation. Are required for counter initialization and counter observation. Counter observation. So some more clock pulses are required for counter initialization and counter observation. Okay. So that is why counter initialization means counter it has to be brought to the initial state, and counter observation means output of the counter it has to be taken to some register and the register has to be read. So that is why in this particular case, if functional team, if only functional verification team exists, then functional team they test the counter using functional patterns. So it will take more than 1000 clock pulses to tell that the counter is failing. The reason is functional verification team they will be checking the functionality. That is, they will check if the counter counts from 0 to 1023. Okay, checking the functionality means they will check if the counter counts from 0 to 1023. So counter is failing at the 1000th pulse. That is, at the 1000th pulse only, counter is again counting 999 instead of 1000. Okay, so counter is again that at the 1000th pulse only, counter is again counting 999 instead of 1000. So 1000 pulses are required for this. And then some more clock pulses are required for counter initialization and counter observation. So counter it has to be brought to some initial state. So that is what is counter initialization. And counter observation means output of the counter it has to be taken to some register and the register has to be read. So some more clock pulses will be required for counter initialization and counter observation. So ultimately, we can say that it will take more than 1000 clock pulses to tell that the counter is failing in this particular case. And then functional verification team, they can only tell that the counter is failing. Okay, so functional verification team, they can only tell that the counter is failing. The reason is they will be checking the functionality. They will be checking the functionality. Okay, so that is they check if the counter counts from 0 to 1023 properly or not. That is, check if the counter counts from 0 to 1023 properly or not. Counts from 0 to 1023 properly or okay. So functional verification team can only tell that the counter is failing. The reason is they will be checking the functionality. They will check if the counter counts from 0 to 1023 properly or not. Okay. So in this case, if you see after counting 999 instead of incrementing to 1000, it once again counts 999. Okay. So in this case, after counting 999, instead of incrementing to 1000. Instead of incrementing to 1000. Incrementing to 1000. It is once again counting 990. It is once again counting 990. Once again counting 999. So that's why counter is failed. Counter is failed. Okay, so functional verification team, they can only tell that the counter is failing. The reason is they will be checking the functionality as we discussed earlier. So they will check if the counter counts from 0 to 1023 properly or not. Okay, they will check if the counter counts from 0 to 1023 properly or not. So in this case, after counting 999, instead of incrementing to 1000, it is once again counting 999. So that's why counter is failing. Okay, so in this case, after counting 999, instead of incrementing to 1000, it is once again counting 999. So that's why counter is failing. Okay. So yeah, that is what they are checking the functionality. They are checking if the counter counts from 0 to 1023 properly or not. So in this case, what is happening after counting 999? Instead of counting 1000, it is once again counting 999. So that's why we can see that the counter is failing. Now, we will try to understand what will happen if a DFT team exists. We'll try to understand what will happen if a DFT team exists. So if a DFT team exists, what will happen? So here in this case, so counter, okay, our scenario is we are having a 10-bit counter with a counter initialization and a counter observation circuit. So scenario is suppose the counter is manufactured with a defect. Okay, suppose counter is manufactured with a defect. So that's why after counting 999, instead of counting 1000, it incorrectly rolls back to 999. Counter is manufactured with a defect. So that's why after counting 999, instead of counting 1000, it incorrectly rolls back to 999. So now if a DFT team exists, then what will happen? DFT patterns are used to test the chip. So if a DFT team exists, then what will happen? DFT patterns are used to test the chip. So DFT will be able to tell that the counter is failing approximately in the range of 100 clock pulses itself. DFT will be able to tell that the counter is failing in approximately in the range of 100 clock pulses itself. Approximately in the range of 100 clock pulses means you can imagine something like 80, 90. You can imagine something like 80, 90, 100, 120, like that, etc. Okay, so DFT will be able to tell that the counter is failing in approximately in the range of 100 clock pulses itself. 100 clock pulses will be somewhere around 80, 90, 100, 120, etc. Okay. So how? How DFT team are able to tell that the counter is failing in approximately in the range of 100 clock pulses itself? How? So it is because DFT team will go for scan insertions. Because of that, we will be easily able to control and observe our circuits. Okay, because of that, we will be easily able to control and observe our circuits. Okay, so we'll try to understand what does this mean. What does this mean? We will try to understand when we do our course. When we do our course, we will try to understand. Okay, so what is scan insertion? If we go for scan insertion, how will we be able to easily control and observe our circuit? So because of that, how in this particular counter example, we are able to tell that the counter is failing in approximately in the range of 100 clock pulses itself. All these things we will do it in our main course. Okay, when we do our DFT course, we will discuss all these points. So DFT will be able to tell that the counter is failing approximately in the range of 100 clock pulses itself. So it can be somewhere around 80, 90, 100, 120, 200 like that. So how is DFT team able to tell that the counter is failing approximately in the range of 100 clock pulses itself? It is because we will be going for scan insertion. Because of that, we will be easily able to control and observe our circuit. Okay, we will be easily able to control and observe our circuit. So if you just observe, DFT team, we require less number of clock pulses. Am I audible? I got a prompt that my voice got disconnected. Am I audible? Okay, yeah, let us continue here. So, if you see DFT team, we require less number of clock pulses compared to the functional verification. Okay, DFT team, we require less number of clock pulses compared to the functional verification team. So that's why test time will be less compared to the functional verification team. So that's why test time will be less compared to the functional verification team. So, which means functional verification team for the same counter example, they had required more number of clock pulses. They had required more than 1,000 clock pulses. They had required more than 1,000 clock pulses. More than 1,000 clock pulses. 1,000 clock pulses. So DFT team, if you see, DFT team, okay, we require approximately in the range of 100 clock pulses. DFT team, we require approximately in the range of 100 clock pulses. Range of 100 clock pulses. Okay, approximately in the range of 100 clock pulses. So functional verification team, they require, in this particular situation, if you see, functional verification team, they had required more than 1,000 clock pulses. DFT team, we require approximately in the range of 100 clock pulses. So as you can see, DFT team, we require less number of clock pulses compared to the functional verification team. The reason is we'll be going for scan insertion, so we will be easily able to control and observe our circuit. So that's why in this particular case, if you see, functional verification team had required more than 1,000 clock pulses, whereas DFT team we require in the range of approximately in the range of 100 clock pulses. So DFT team we require less number of clock pulses compared to functional verification team. So that's why test time will be less compared to the functional verification team. So that's why test time will be less compared to the functional verification team. Okay. And DFT team will be able to tell that the counter is failing and also tell what manufacturing defect has caused the counter to fail. So DFT team will be able to tell that the counter is failing and also tell what manufacturing defect has caused the counter to fail. So how? How is that? So DFT team will be able to tell that the counter is failing and also tell what manufacturing defect has caused the counter to fail. So how? So this is the additional detail which the DFT team is able to tell what manufacturing defect has caused the counter to fail. So DFT patterns, they are generated using ATPG. DFT patterns, they are generated using ATPG. So ATPG tool does a technique called as fault simulation in order to generate the test patterns. So what is fault simulation technique? We will understand it when we do the this one. We will understand it when we do our course. You will be able to understand what is fault simulation technique. So as DFT patterns are generated using this fault simulation technique only, if we will be able to tell what manufacturing defect has caused the chip to fail. So DFT will be able to tell that the counter is failing and also tell what manufacturing defect has caused the counter to fail. How are we able to give that additional detail? It is because DFT patterns are generated using ATPG and ATPG tool does fault simulation to generate the test patterns. ATPG tool does fault simulation to generate the test patterns. Okay. So conclusion is with the DFT patterns, test time will be less compared to the functional patterns. As we saw in that counter example, functional verification team had required more than 1,000 clock pulses, whereas DFT team had required approximately in the range of 100 clock pulses itself. Okay, so with the DFT patterns, test time will be less compared to the functional patterns. And DFT will be able to tell what manufacturing defect has caused the chip to fail. So that is what we have seen here, right? DFT patterns are generated using ATPG. So ATPG tool does fault simulation to generate the test pattern. So functional verification team, they can only tell if the chip has passed or failed. Whereas DFT team will be able to tell that the chip has passed or failed and also tell what manufacturing defect has caused the chip to fail. Because DFT patterns, they are generated using ATPG. ATPG tool does fault simulation to generate the test patterns. So that's why DFT will be able to tell what manufacturing defect has caused the chip to fail. Okay. So as DFT patterns has these advantages over functional patterns. As DFT patterns has these advantages over functional patterns, DFT patterns will be used to test the chip after manufacture. Some functional patterns will also be used to test the chip after manufacturing, but majority DFT patterns will be used to test the chip after manufacturing. Okay, as DFT patterns has these advantages over functional patterns, DFT patterns will be used to test the chip after manufacturing. So some functional patterns will also be used to test the chip after manufacturing, but majority DFT patterns will only be used to test the chip after manufacturing. Okay. And if DFT patterns are used to test the chip after manufacturing, why do we need a functional verification team? So in this slide, we had seen that DFT patterns, they are having advantages over functional patterns. So DFT patterns will be used to test the chip after manufacturing. So if DFT patterns are used to test the chip after manufacturing, why do we need a functional verification team? So can anyone guess? If DFT patterns are used to test the chip after manufacturing, why do we need a functional verification tool? Any guesses? So if DFT patterns are used to test the chip after manufacturing, why do we need a functional verification tool? Any guesses? So I'll give you some time now. Time is 3:08. Let me just give you time till 3:10. Can anyone think and say if DFT patterns are used to test the chip after manufacturing? Why do we need a functional verification? So you can try and you can think and you can try to tell your answers.
అసలా ల్యాప్టాప్ ఏందో నా ఫోన్ ఏందో నెట్ అట్లా ఆడియో కనెక్ట్ అవ్వట్లా నాకేమీ వినపడదు ఏంటిది అయిపోలే ఇంకా ఆమె ఏం చెబుతుంది టాప్ టాప్ కట్ అవుతుంది ఆగిపోతుంది కట్ అవుతుంది ఆగిపోతుంది
Someone's microphone is unmuted. Can you mute yourself?
ఏంటిది నేది హాట్స్పాట్ నేమ్
Okay, so let me just try to provide the answer here. So if DFT patterns are used to test the chip after manufacturing, why do we need a functional verification tool? So if DFT patterns are used to test the chip after manufacturing, why do we need a functional verification tool? So consider the below scenario. So here we are having a half adder. So I've considered sum is equal to a plus b, carry is equal to ab. Whether this is a correct expression, can anyone tell? For half adder, whether this is a correct expression?
No.
Yes. So what should be the correct expression? Sum should have been a XOR b. But here this is someone has written sum is equal to a plus b. This is a functional fuck. Okay. So now for time being, assume that you don't have a functional verification tool. Okay. For time being, assume that you don't have a functional verification tool. So what will happen? The design, it has got synthesized. So like this, it has got synthesized. So if you see the wrong design has got synthesized. And then it will be given to the DFT team. So DFT team, we will be generating the patterns just to check whether there are any manufacturing defects in each and every note of the design. And then what will happen? The chip will be manufactured. And then the DFT patterns, they are actually applied. And then the output of the chip, it is compared with the expected value. So output of the chip, it is equal to the expected value, which means there are no manufacturing defects. Output of the chip, it is equal to expected value, which means there are no manufacturing defects. But whether the design will function like a half adder, so output of the chip, it is equal to expected output, it means that there are no manufacturing defects. But whether the design will function like a half adder, can anyone guess whether there are no manufacturing defects, but whether this design will function like a half adder? Can anyone guess and tell? So can anyone guess? There are no manufacturing defects, but whether the circuit will function like a half adder? So it will not function. Yes, correct. Yes, correct, Shreya. Your answer is correct. So it will not function like a half adder. So it will not function like a half adder. Okay, so even though there are no manufacturing defects, the circuit will not function like a half adder. Why? The design itself is wrong. So this is what is the significance of the functional verification team. So this is what is the significance of the functional verification team. They will be validating the functionality. So whatever is written here, whether this is correct or not. Okay, so that is what. So in this case, there are no manufacturing defects. But whether the circuit will function like a half adder? No. Because even though there are no manufacturing defects, the circuit will not function like a half adder because the design itself was wrong. In the design stage itself, sum was written as a plus b. So the design itself was wrong. So this is what is the significance of functional verification team. They will be validating the functionality. So whatever is written here, whether this is correct or not. So that is what will be validated by the functional verification. Okay. And then we will try to understand about testing. So we had seen about this testing in the ASIC flow slide, right? In the ASIC flow, we had seen a slide where we had written, like a phase where we had written about testing like this. So in the ASIC flow slide, we have discussed about this testing, right? So this one, the last page, packaging and testing. So we have discussed about the testing. So let's try to discuss here. So what is testing? So as you know, as we saw in the ASIC flow slide, so this is actually done after manufacturing. Okay. So testing, it is actually a process of determining whether a device is good or not. So testing is a process of determining whether a device is good or not. So in our case, it is actually to check if our chip is good or not. So it is actually to check if our chip is good or not. If our chip is good or not. So that is to check whether there are any manufacturing defects or not. That is to check whether there are any manufacturing defects or not. Whether there are any manufacturing defects or not. Manufacturing defects or not. Okay, so testing is a process of determining whether a device is good or not. So which means it is actually to check if our chip is good or not. That is to check whether there are any manufacturing defects or not. So testing includes test pattern generation, application, and output evaluation. So these test patterns, they are actually generated by the DFT engineer. Before manufacturing itself will be generating the test patterns. So it will be consisting of the input sequence. Someone's microphone is unmuted. Can you mute yourself? So these test patterns, they are actually generated by the DFT engineer before manufacturing. So it will be consisting of input sequence and expected output. So what will happen? This input sequence, it will be applied onto our chip. The input sequence will be applied onto our chip, and then the output of the chip, it will be compared with the expected output. Output of the chip, it will be compared with the expected output. So output of the chip, if it is equal to the expected output, it means that the chip is good. There are no manufacturing defects. So output of the chip, if it is equal to the expected output, it means that the chip is good. There are no manufacturing defects. Output of the chip, if it is not equal to the expected output, it means that the chip has failed. So there are some manufacturing defects in the chip. Okay, so these test patterns, it will be generated by the DFT engineer before manufacturing itself will be generating the test pattern. So it will be consisting of the input sequence and expected output. So we will be applying this input sequence onto our chip, and then the output of the chip, it will be compared with the expected output. So the output of the chip, if it is equal to the expected output, it means that the chip is good. So there are no manufacturing defects. And output of the chip, if it is not equal to the expected output, it means that the chip has failed. So there are some manufacturing defects in the chip. So if a particular chip fails, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. Okay, if a particular chip fails, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. So testing, it is a process of determining whether a device is good or not. So to check if our chip is good or not, that is to check whether there are any manufacturing defects or not. So testing includes test pattern generation, application, and output evaluation. So these test patterns, they are generated by the DFT engineer before manufacturing. So it will be consisting of the input sequence and expected output. So the input sequence, it will be applied onto the chip, and then the output of the chip will be compared with the expected output. So output of the chip, if it is equal to the expected output, it means that the chip is good. There are no manufacturing defects. So output of the chip, if it is not equal to the expected output, it means that the chip has failed. So there are some manufacturing defects in the chip. So if a particular chip fails, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. Okay. And what are these manufacturing defects? Manufacturing defects means they are the defects that are caused due to process variations and random imperfections. So what are process variation? Process variation means slight variation in the transistor channel length. Slight variation in the transistor channel length, in the transistor channel length, okay. Metal interconnect width and thickness, metal interconnect width and thickness, width and thickness, okay. So all those things will actually impact the logical and timing performance. So all these things can actually impact the logical and timing performance. Logical and timing performance. Okay. And then random imperfections means It can result in shorts, opens, unintentional shorts, unintentional opens, all those things. It can result in unintentional shorts, unintentional opens, etc. Okay. So defects that are caused due to process variation and random imperfections. So process variation means slight variation in the transistor channel length, metal interconnect width and thickness, all those things. It can impact the logical and timing performance. Random imperfections means it can result in shorts, opens, all those things. Okay. And the next one is the flow of DFT. So flow of DFT. So first is insertion. So insertion means adding extra logic. So insertion means adding extra logic. And then generation, so which is nothing but patterns. Patterns will be generated. So input data and expected output will be generated. And then we have the simulation. Simulation means before delivering the test patterns generated during ATPG to test the chip after manufacturing, we need to validate once whether proper patterns are generated or not. Okay. So before delivering the patterns, before delivering the patterns, delivering the patterns, delivering the patterns. Okay. So before delivering the patterns generated during ATPG, generated during ATPG to test the chip after manufacturing. Test the chip after manufacturing. Okay. We need to validate once whether proper patterns are generated or not. We need to validate once whether proper patterns are generated or not. Whether proper patterns are generated or not. So that validation is only called as simulation. So before delivering the patterns generated during ATPG to test the chip after manufacturing, we need to validate once whether proper patterns are generated or not. So that validation is only called as simulations. Okay. And this is what is our course outline. So in our course outline, first we have scan insertion, then scan compression, then on-chip clock controller OCC, automatic test pattern generation ATPG, simulations. So in simulation, as of now in our DFT course curriculum, only no timing simulation is covered. So only no timing simulation is covered. No timing simulation is covered. So as of now in our course curriculum, in simulation, only no timing simulation is covered. And then JTAG. JTAG is Joint Test Action Group. So it's actually a IEEE 1149.1 standard. In our course, we will also be covering IJTAG, which is nothing but IEEE 1687 standard. IEEE 1687 standard. And then MBIST. MBIST stands for Memory Built-in Self-Test. And we have boundary scan. V-scan, boundary scan. So boundary scan, we will only be discussing it theoretically. Only theoretically we will be discussing it. Okay, boundary scan, we'll be discussing it only theoretically. So in the upcoming slides, okay, let me just try to discuss more in detail. Like, scan insertion means what are the subtopics will be covered within scan insertion. So I'll give you more details of our course curriculum. Like say, for example, scan insertion means what are the subtopics of scan insertion. Scan compression means again what are the subtopics, like that. I will give you a more detailed idea in the upcoming slides. Okay, so maybe we can have a break for 10 minutes. We can have a break, and then after the break, let us try to see our course curriculum more in detail. Like under each topic, what are the subtopics we will be covering it, we'll try to understand. Okay. So yeah, now time is 3:25. We can have a break till 3:35 and we can continue after the break. Okay. So thank you all. We meet after the break at 3:35. We can have a break for 10 minutes.
This conference will now be recorded.
Okay, so good afternoon all. We will continue with our session. Can anyone confirm if I'm audible and is my voice clear?
Voice is clear.
Okay, so now let us continue with that session. So I'll give you like more details about the course outline. So what all the things will be covered in our course. So let me just give you more details on it. So the first topic which we are going to cover is scan insertion. Okay, so the first topic which we are going to cover here is scan insertion. Okay, so under scan insertion, so let me just write that. Topic 1 is scan insertion. So under scan insertion, we will be covering what is a scan cell and its functionality, scan cell functionality, and then we will cover the scan chain functionality. Okay, we'll cover the scan chain functionality, and we will cover, so like basically like scan insertion. What is scan insertion? So we'll try to understand like what is scan insertion. So what is scan insertion? We will understand. While understanding what is scan insertion, we'll try to understand what is a scan cell, how does a scan cell function, what is a scan chain, how does a scan chain function. Okay, and then we'll try to understand the need of scan insertion, need of scan insertions. So why do we need to go for scan insertions? We will try to understand. And then we will be discussing like scan design rule checks. So scan DRCs. DRC stands for design rule checks. Design rule checks. So DRC stands for design rule checks. We'll try to understand what are scan DRCs. Okay, what are scan DRCs? We will try to understand. What are the design rule checks? We will try to understand. And we'll try to understand about the various scan DRC. So we'll understand what is DRC, what is scan DRC, why it is used. We'll understand. And we will try to understand the various scan DRCs. Like we'll try to understand about the clock controllability DRC. Okay. So we'll try to understand about the clock controllability DRC. Clock controllability DRC. And then set reset controllability DRC. So set reset controllability DRC. And then feedback loop DRC. Feedback loop DRC. And then potential race DRC. Potential race DRC. And then bus contention. Bus contention. These are all the various scan DRCs. So we will discuss about the various scan DRCs. So scan DRCs. DRC stands for design rule checks. What are scan DRCs? First, what are scan DRCs? We'll try to understand. And we'll try to understand about the various scan DRCs like clock controllability DRC, set reset controllability DRC, feedback loop DRC, potential race DRC, bus contention DRC. So we'll try to understand about the various scan DRCs. And then we will also try to understand scan chain balancing. We'll also try to understand what is called as scan chain balancing. Okay, we'll try to understand what is scan chain balance. So in scan chain, that is what we'll understand what is scan chain balancing. Okay. Why do we need to go for scan chain balancing? How to achieve scan chain balancing? All these things we will try to understand. So what is scan chain balancing? Why do we need to go for scan chain balancing? And how to go for scan chain balancing? So while understanding how to go for scan chain balancing, we will try to understand what is edge mixing. What is edge mixing? And what is domain mixing? Try to understand what is edge mixing and what is domain mixing. What is edge mixing and what is domain mixing? We will try to understand. And yeah, that is what. So how to achieve scan chain balancing? At that time, we'll understand what is edge mixing, what is domain mixing. We'll try to understand. Okay. And we will also try to understand. Next, what we will understand is if we go for edge mixing and domain mixing, it will again introduce some problems. So what problems edge mixing and domain mixing will introduce and what should be its solution, we will try to understand. So problems in edge mixing and domain mixing, and then its solutions. And then its solutions. Okay. So we'll, in scan chain balancing, we will try to understand what is scan chain balancing, why do we need to go for scan chain balancing, and how to go for scan chain balancing. So if you see, while understanding how to go for scan chain balancing, we'll try to understand what is edge mixing and what is domain mixing. And if you go for edge mixing and domain mixing, again, it will introduce some problems. So what problems edge mixing and domain mixing will introduce and what should be the solution of those problems? We will try to understand it as a next topic. And apart from that, we will also be discussing some small topics like what is it, scan chain reordering, some small topics like scan chain reordering. These topics also we will be covering. Okay, so this is it. So we'll be covering, like these are all the subtopics we will be covering within the scan insertion topic. Okay, these are all the subtopics which we will be covering within the scan insertion topic. And then we'll try to see the next topic. Next topic is nothing but scan compression. So topic 2 is scan compression. Topic 2. So topic 2 is scan compression. Scan compression. Okay. So in topic 2, in scan compression, it is also called as EDT insertion. Scan compression is also called as EDT insertion. So we will understand, first we will understand what is scan compression. Okay. And then we will try to understand why do we need to go for scan compression? Why do we need to go for scan compression? Okay. And then there will be a quantity called as compression ratio. There will be a quantity called as compression ratio. Compression ratio. So we will try to understand about this compression ratio quantity. So we'll try to understand what is this compression ratio. Okay. And we'll try to understand what are the merits and demerits of high and low compression ratio. What are the merits and demerits of high and low compression ratio? Demerits of high and low compression ratio. High and low compression ratio. We'll try to understand. Okay, so what is compression ratio and what are the merits and demerits of high and low compression ratio? We'll try to understand. Okay. And then we will be like, when you want to achieve scan compression, if you are using mentor graphics tools, we will be adding up a logic called as EDT logic. The full form of EDT is embedded deterministic test. Deterministic test. Embedded deterministic test. So which is nothing but the EDT logic, embedded deterministic test. So if you want to achieve scan compression, if you are using mentor graphics tools, you will be adding up a logic called as EDT, embedded deterministic test. Now EDT logic, it has various components like decompressor and then compressor, and then controller, and then bypass logic. Like the EDT logic, it has various components like decompressor, compressor, controller, bypass logic. Like that, EDT logic has various components. So we'll try to understand about each component. We'll try to understand about each component and what role it plays in scan compression. We'll try to understand. We'll try to understand about each component and we'll try to understand what role it plays in compression. Okay. And then we will also discuss some topics like pipeline flops in compressor, lockup cells in EDT, like that. Few more topics we'll try to understand. So pipeline flops in compressor, and then lockup cells in EDT, lockup cells in EDT, like this. Okay, so all these things we will understand. So under scan compression, we'll first try to understand what is scan compression, why is scan compression needed. So what is the quantity called as compression ratio? So what is it? What are the merits and demerits of high and low compression ratio? And if you want to achieve scan compression, if you are using mentor graphics tools, you will be adding up a logic called as EDT logic, embedded deterministic test EDT logic. So you'll be having 4 components within that EDT logic, like the compressor, controller, bypass logic and all. So we will try to understand the structure of each component, and we'll also try to understand what role it plays in scan compression. And then we'll try to understand about the pipeline flops in compressor, and then lockup cells in EDT. So all these things we will try to understand. Okay. And the next topic. So next topic 3 is ATPG. So topic 3 is ATPG. So topic 3 is ATPG. So under ATPG, we will try to understand what is ATPG. We'll try to understand what is ATPG. Okay, we'll try to understand what is fault simulations. Okay, we'll try to understand what is fault simulation. These things we'll try to understand. We'll try to understand what is ATPG, what is fault simulation, we'll try to understand. And then we'll cover the various fault models. We'll cover the various fault models. Okay, so we will cover like stuck at fault model, and then we will cover transition delay fault model, and then we'll cover path delay fault model. So this transition delay fault model and path delay fault model, we will be calling it as at speed test. At speed test. And then we'll also try to understand IDDQ fault model. These are all the fault models we'll cover. We'll cover what is stuck at fault model, what is transition delay fault model, what is path delay fault model. So transition delay fault model and path delay fault model, we call it as at speed test. And then we'll try to discuss on the IDDQ fault model. Okay. And the next, we will also try to discuss about what is fault dominance. Okay, fault dominance, fault equivalence, fault collapse, okay, fault dominance, fault equivalence, fault collapse. Okay, we'll try to understand like fault aliasing, fault aliasing. We'll try to understand what is coverage, what is fault coverage, what is test coverage. Okay, we'll try to understand coverage analysis and improvement, coverage analysis and improvement. Okay, we'll try to understand what are test point insertions, test point insertions. Okay, we'll try to understand how patterns are classified. So pattern classification. Okay, and one more important thing, we'll also try to understand about the fault classes. So fault classes. So faults, they are broadly classified as testable and untestable. Under untestable, it is again classified as unused, tied, blocked, redundant. We'll try to understand what are all these things. Under testable, we'll try to understand what is detected, possibly detected, ATPG untestable, undetected. All these things we'll try to understand. Okay, we will also try to understand the OCC architecture, placement of OCC. All these things we'll try to understand. On chip clock controller, OCC architecture, placement of OCC, placement of OCC. So all these things we'll try to understand. Like I've just given a high level like overview. Like we'll be covering some more topics as well within that ATPG. So say for example, TDF means we'll be covering ways to detect TDF like TDF LOC, TDF LOS. So there's ways to detect TDF, like that. Various things we will be covering it. Okay, so ATPG is actually a very vast topic. So many topics will be coming under ATPG topic. I'll just try to given you an high level idea about what all the topics we'll be covering it in our ATPG topic in our course. So what all the topics we'll be covering, I'll just given a high level idea. So we will be covering like many more topics are actually there in ATPG, which we will be covering. Many more small topics will be covered within ATPG. So yeah, ATPG is actually a very vast topic. So these are all the main subtopics which we will be covering in the ATPG topic. Okay. And next topic is simulations. So next topic is simulations. So topic 6 is simulations. Sorry, topic 4 is simulations. So again, in simulations, we will try to understand what is simulation, why do we need to go for simulations, what is the flow of simulations, what are serial simulations, what are parallel simulations, okay, serial and parallel simulations, why it is required. Okay, so what is serial simulation, what is parallel simulation, why serial and parallel simulations are required. Okay, and then we will try to understand about the simulation mismatch debug. We will try to understand about the simulation mismatch debug. So these are all the topics which is there in our course curriculum. Apart from that, I'll be covering few extra topics in simulations, like scenarios which will cause, scenarios which will cause. One is serial simulation to pass, and parallel simulation to fail. Parallel simulation to fail, and which scenarios will result in serial simulation to fail and parallel simulation to pass. Okay, so this is an extra topic which I'll be covering. So these are all the topics which we will be covering it in our simulation topic. And then we will also be discussing on the next topic. So topic 5 is JTAG. So topic 5 is nothing but JTAG. So topic 5. So topic 5, the first subdivision, topic 5A, let me consider, we'll be discussing about JTAG. So JTAG, it is an IEEE 1149.1 standard. So JTAG is IEEE 1149.1 standard. Okay. So what are all the things we will be covering? So we'll be covering the need of JTAG, and then we will be covering the JTAG tap architecture, JTAG tap architecture, and then we will be covering the JTAG controller, So JTAG controller will be a 16-state FSM. JTAG controller will be a 16-state FSM. So these are all the topics we will be covering. We'll be understanding about the various states in this JTAG FSM. All these things we will try to understand. So we'll try to understand what is the need of JTAG, what is a JTAG tap architecture. So JTAG controller will be a 16-state FSM. What are the 16 states in that 16-state FSM? All these things we will try to understand. And then, as I told, we'll also be covering IEEE 1687 standard. 1687 standard, which is nothing but IJTAG. We'll also be covering the IEEE 1687 standard, which is nothing but IJTAG. So we'll be understanding the architecture. Okay, we will be understanding the architecture, and then we will be doing a comparison between JTAG and IJTAG. Okay, we'll be doing a comparison between JTAG and IJTAG. Okay, and then we will be discussing the advantages of IJTAG. So these things we'll cover. So IEEE 1687 standard IJTAG. So we'll understand the architecture. What is the comparison between JTAG and IJTAG? After doing a comparison, we will try to understand what are the advantages of IJTAG. All these things we will cover. Okay, and then in topic 5B, we will be discussing about boundary scan. B scan is nothing but boundary scan. Okay, so under boundary scan, we will be covering like what is boundary scan. Okay, we'll be covering what is boundary scan, what is the need of it, what is the structure of boundary scan cell, and then we will try to understand about the modes of operation of boundary scan cell, Okay, we'll try to understand about the modes of operation of boundary scan cell. We'll understand about these instructions like XTest instructions, sample preload instruction, sample preload, bypass. We will understand these instructions. XTest, sample preload, bypass. So we will try to understand about these instructions. Okay, so these are all the topics which we'll be covering it under boundary scan. What is boundary scan? What is the need of boundary scan? What is the structure of boundary scan cell? Okay, modes of operation of boundary scan cell. What is XTest instruction? What is sample preload instruction? What is bypass instruction? All these things we will try to understand it when we do the boundary scan topic. And then we'll be discussing the next topic is we'll be discussing about MBIST. So topic 6 is we will be discussing about MBIST. Topic 6 is we will be discussing about MBIST. Okay. So MBIST stands for Memory Built-in Self-Test. Okay, MBIST stands for Memory Built-in Self-Test. Memory Built-in Self-Test. Built-in Self-Test. So under MBIST, we will cover the basics of memories. Basics of memories. Like what is a RAM, what is a ROM, what is SRAM, what is VRAM, like that. Some basics of memories we'll cover. And then we will go into what is required for a DFT engineer. So which means we will move ahead with memory fault models. We will go ahead with memory fault models. Okay, so in memory fault models, we'll try to understand what is duck-cat fault model, what is transition fault model, what is address decoder fault model, what is coupling fault model. All these things we will understand. So we'll understand the basics of memories. And then we'll understand the memory fault models, like what is duck-cat fault model, what is transition fault model, what is address decoder fault model, what is coupling fault model. All those things we will understand. And then memories, they will be tested using generalized algorithms. So memories, they are tested using generalized algorithm. Tested using generalized algorithm. Like we will be discussing about various algorithms like 0-1 algorithm, 0-1 algorithm, and then checkerboard algorithm, checkerboard algorithm, and then MATS algorithm, MATS plus algorithm, MATS plus algorithm, March X algorithm, March C algorithm. So for each algorithm, we'll try to understand what is the sequence. So each algorithm will be having a specified sequence. So what is the sequence of each algorithm? So which algorithm will be able to cover which faults in memories and how that particular algorithm is able to cover? We'll try to understand. Okay, so we will try to understand which algorithm will be able to cover which faults in memories. Will be able to cover which faults in memories. Which faults in memories and how that particular algorithm will be able to cover that. We will try to understand. So we will be having various algorithms. So as I told, we'll be having the 0-1 algorithm, checkerboard algorithm, MATS plus, March X, March C, like that. So for each algorithm, we will try to understand the sequence and we'll try to understand which algorithm will be able to cover which faults in memories and how. And we'll also try to understand why memories are tested using generalized algorithms. Why memories are tested using generalized algorithms also we will try to understand. And then we will try to understand about descent MBIST. We'll try to understand about descent MBIST. So under descent MBIST, we will try to understand MBIST implementation and architecture. Descent MBIST implementation and architecture. Implementation and architecture. Okay. And then we will try to understand about the Tessent MBIST operation protocol. Tessent MBIST operation protocol. Okay. So when we discuss about the Tessent MBIST operation protocol, we will also try to understand about these various signals, like this setup signal, this setup, and then MBIST PG enable, MBIST PG enable, and then go bit, done bit. Okay, so all these signals we'll try to understand. We'll try to understand the BIST setup signal, MBIST PG enable signal, go bit, done bit. So all these things we will try to understand. And then we will try to understand the group concept of group, and we'll try to understand the concept of step. We'll try to understand the concept of group, and we'll try to understand the concept of step. Okay, so these are all the things which we will cover within Tessent MBIST. So we'll try to understand the Tessent MBIST implementation and architecture, Tessent MBIST operation protocol, like this setup, MBIST PG enable, go, done, group, step. Okay, I'm sorry. Under Tessent MBIST operation protocol, we'll try to understand about these signals, like this setup, MBIST PG enable, go signal, done signal, all those things we'll try to understand. We'll try to understand the concept of group. We'll try to understand the concept of step. All these things we will understand it within Tessent MBIST. Okay, so these are all the topics which we will be covering in our course. And whatever I told now, it was from theory side. So in labs, we will be covering these things in our labs. So in our labs, we'll cover JTAG, MBIST, scan insertion. So there are basically two approaches in scan insertion. So one will be the top-down approach and the other one will be the hierarchical scan. So we will understand both. Okay, so both the approaches we will try to understand. So EDT and OCC insertion, and then ATPG pattern generation. So ATPG and MBIST simulations. So all these things we will try to understand. And let me just try to give you a more detailed explanation about the labs. So let me just open this document. One second. Yeah. So basically, DFT projects. So they are like divided into 4 levels. So in level 1 and level 2, we'll be having simple labs. And in level 3 and level 4, we'll be having designs with higher complexity. So it can be projected as a project work in your resumes. Okay, so basically in our DFT course, the projects, they are actually like divided into 4 levels. So in level 1 and level 2 are simple labs. Level 3 and level 4 are designs with higher complexity. So it can be projected as a project work in your resume. So in level 1 projects, what we will be doing is, in level 1 projects, we'll be performing scan insertions on level 11 simple designs. Okay, so we'll be performing scan insertion on 11 simple designs. So flop count, it will be only around of 100 in that range. Okay, that's why I told these are simple designs. Flop count will only be in the range of around 100, 200, like that. The flop count will be there. So our aim in this level 1 projects is, we need to understand scan insertion and its mean, and we need to understand the flow of scan insertion. So flow of scan insertion means, like, we are going to use metagraphics tools in our lab. So if you want to perform scan insertion, if you want to implement scan insertion using the metagraphics tools, which is nothing but the Tessent tools, you need to follow a procedure. You need to follow a procedure if you want to perform scan insertion using Tessent tools. So that procedure is only called as flow of scan insertion. So basically, you will be having setup phase, analysis phase, insertion phase. So when we do the labs, you'll be able to understand. when we do the labs, we'll be able to understand like what is the setup phase, what is analysis phase, what is insertion phase, what we are going to do in each phase. You'll be able to understand. This is the procedure. You need to follow a procedure. When you want to do scan insertion using test tool, you have to follow a procedure. So that is what is called as flow. And then you need to check for the various DRCs. Okay, we'll be checking for the various DRCs. If you get any DRC violation, we'll be analyzing those DRC violations in the schematic. So these are all the DRC violations which we will be discussing in our labs. So clock controllability and set reset controllability DRC. In test and tools, it will be pointed as S1, S2 violation. Clock data race DRC. In test and tools, the code is C6. Bus contention in test and tool code is E10. C3 violation. Pre-existing scan chains in test and tools, its code is S6. Okay, likewise. Same way we will try to see if in case you get any DRC violations, what are the ways with which you can resolve it. So one is manual editing of netlist. Other one is we can make use of these commands. Other one is auto fix method. So what are all these methods and how by using all these methods you will be able to resolve the DRC violation. We will compare each method and see and which one is more preferred and why it is more preferred. All these things we will try to discuss. And we'll also try to discuss how to achieve scan chain balancing using edge mixing and domain mixing. All those things we'll try to understand. How to insert lockup cells, we'll try to understand what are lockups, how to insert it. And various output reports and outputs of scan insertions, what the tool has dumped out, we'll try to understand. Okay, we'll try to understand what the tool has dumped out, the reports and outputs of scan insertion. What are the things the tool has dumped out, we'll try to understand. So whatever scan chains we have inserted, we can trace it in the schematic. So all these things we can do it with the level 1 projects. So level 2 projects, what we are going to do is, for the same 11 test cases for which we had performed scan insertion in level 1 projects, right? So for the same 11 test cases, we will perform EDT insertion, that is nothing but scan compression, ATPG and simulations. And what are the things we need to learn? So we'll be learning like scan compression. What is EDT insertion? We'll try to understand. Okay, scan compression and its mean. What are the inputs and outputs of scan compression? Okay, EDT insertions, that is what. So what is the flow of EDT insertion in test and tool? So if you want to do EDT insertion using test and tools, you have to follow a procedure. So that procedure is only flow of EDT insertions. So certain configuration, how to decide certain configurations like how to decide the number of internal chains and external channels. What are the merits and demerits of high and low compression ratio? We'll understand about each of these components of the EDT hardware. So all these components in the EDT hardware we'll try to understand. We'll also trace this EDT hardware in the schematic, whatever EDT hardware we have inserted. We can also trace that in the schematic and we will try to see. We can also try to understand what are pipeline flops, why pipeline flops are required, and how to insert pipeline flops in the compressor logic. All those things we will try to understand. And then in ATPG, we will try to understand ATPG and fault simulation. So what is the procedure, flow, that is the procedure of doing ATPG in test and tools. We'll be working on stuck-at fault model, transition delay fault model, and IDDQ fault model in our labs. Okay, for all these fault models, we'll be generating the patterns. So we'll be generating patterns with EDT as well as we'll be generating the bypass patterns. We'll understand what is patterns with EDT, what are bypass patterns. So why do we need to generate bypass patterns? How to generate bypass patterns? Like that, we will discuss all these things in our labs. And we'll also be working on this fault classes. We'll understand this complete fault classes. Okay, I had already told in the theory part as well, right? We'll be understanding about these various fault classes. So understanding of these fault classes will be very important for working on coverage analysis and coverage improvement. Okay, already in the theory sections of topics, I would have told about these fault classes. So we'll be discussing about these fault classes. These are very important for understanding the coverage analysis and coverage improvement. Okay, so that is what we'll understand the concept of coverage. What is test coverage? What is fault coverage? We will work on coverage analysis for various fault classes like pin constraint, sequential depth, MPO, EDT abort, and we will see various coverage improvement techniques like increasing sequential depth, doing test point insertion, bypassing the memories. Like that, we will see various coverage improvement techniques. Okay, determining correct compression ratio using unless compression command. So likewise, we will be discussing the various coverage improvement techniques. So there is an automatic flow of adding test points using testing tools. We will also be understanding that. So what are test points and what is the automatic flow with which you can add test points using testing tools, we will understand. Or if you want to do test point insertion using tickle scripts, how to do it, we will understand. Okay, we will try to understand various ATPG DRCs. So what are ATPG DRCs? And we'll try to understand some important DRCs like basic violation, D1 violation and all we'll understand. Okay, so these things we will try to understand it during the ATPG class. And simulations both with the theory concept of simulation, we'll be doing it by practically demonstrating in the lab. So same as what I had already explained in the theory portion. So simulation and its need. So like what is the flow of simulations using the Sim tool? What is the difference between serial and parallel simulation and why we require both? How to analyze the waveforms? If in case there is any simulation mismatches, how to do the debug? So these things. So the concept of simulation we will be understanding by practically demonstrating it in the labs. Okay. And next comes the level 3 projects. Level 3 and level 4 projects, these are actually designs with higher complexity. So you can actually project this level 3 and level 4 projects as a project work in your resume. So level 3 projects is nothing but hierarchical scan. Okay, level 3 projects is nothing but hierarchical scan. So to work on hierarchical design with a parent core core B and multiple child cores core A. So flop count will be around 4K. So we'll be performing MBIST insertion, scan chain stitching, DRC cleanup, EDT and OCC insertion, ATPG coverage analysis, pattern generation, serial and parallel scan pattern simulation. All these things will be doing. And this is our configuration. So flop count will be around 4K. We'll be having 3 functional clocks, 1 scan clock, and then compression ratio for core A is 8x, for core B is 10x. So this is what is our design configuration for level 3 projects. And what are the things we'll be learning is we'll be understanding what is hierarchical scan. So if you have hierarchical scan, then you have the concept of scan wrappers. What are shared wrappers? What are dedicated wrappers? What are wrapper chains? What is in-test? What is X-test? What is pattern retargeting? So all these concepts would come when you go for hierarchical scan. So we will be understanding about all these concepts, both theory as well as practicals we will try to understand. Okay. And in level 3 projects, we are going to do the TSDB flow. We'll understand about the TSDB flow. What is TSDB? Essential database is TSDB. So what is TSDB flow? We will understand. And we'll be working on MBIST and IJTAG insertion in RTL. So MBIST logic will be inserting the controller interface and BAP. In IJTAG logic will be inserting SIB STA, SIB SRA, SIB MBIST, CBDT, OCC, TDR, SRA control. All these things we will insert. So we'll do the grouping of memories, and we'll also practically divide the memories in different steps. We will control various signals, like these various static signals. We will control it using TDR. What is TDR? You'll be able to understand it. Okay, later. Okay, same way. MBIST pattern specification. So MBIST simulation mismatch. Okay, and then EDT and OCC insertions. Okay, and then scan insertions. So while understanding scan insertion only, we'll understand about scan wrappers, what are shared and dedicated wrappers. Okay, so while doing ATPG, we'll understand what is in-test, what is X-test. We'll also try to understand what is pattern retargeting. So these are all the various concepts and things which we'll be working on our level 3 projects. Okay, and next what we will do is, next, let us see about the level 4 projects. So level 4 projects is nothing but the flat scan. Okay. So like we'll be having a flop count of around 44K. Same will be performing MBIST insertion, scan chain stitching, DRC cleanup, EDT and OCC insertion, ATPG coverage answers will be working on. And this is what is our configuration. So like flop count will be having around 44K. We'll be having 1 functional clock whose frequency is 400 megahertz, 1 scan clock whose frequency is 25 megahertz, and compression ratio will be around 53x. So we'll try to understand what is the difference between hierarchical scan and flat scan. Hierarchical scan was level 3 projects, flat scan is level 4 projects. So what is the difference between hierarchical scan and flat scan? And rest of the things will be the same. MBIST and IJTAG insertion, debugging, simulation mismatches. We'll try to understand what is pin mux logic. EDT and OCC insertion, ATPG and scan insertions and ATPG. So while understanding the scan insertion in ATPG, we will try to understand the differences between the level 3 and level 4 projects. We will try to understand. Okay, what are the differences between level 3 and level 4 projects? We will try to understand. Okay, so this is what we will be working on our labs. Okay, so I just try to give you an overview about the labs as well. And the tools which we will be using is, so like for MBIST, we'll be making use of the meta graphics tools. So MBIST will be making use of test and MBIST, scan will be making use of test and scan, EDT will be making use of test and test compress, ATPG also test and test compress, simulation will be making use of Quest. Okay. And then who can attend this course? So like if you're a student in final semester, if you're seeking DFT as their course curriculum, you can attend. Or a new college graduate who's from relevant branches of engineering and science. Lecturers or professors who want to switch into real-time industry experience. Working professionals from similar or other VLSI domains. So you can all attend the course. And placement support, like we are having tie-up with various VLSI companies. So like you will be, during the course, we'll be providing you with various assignments, mock interviews, presentation session, tests, and also in the day-to-day class interactions will happen. So based on that, you will be like added into a group called as a job support group. And in the job support group, the placement opportunities will be posted. Okay, so students are entitled to placement support based on their performance in the course assignment or as day-to-day interaction in class, mock interviews, tests, all those things. Okay, based on all those things, you will be added, based on your performance in all those things, you'll be added into a job support group, and there the placement opportunities will be posted. And then mock interviews will also be conducted so that you will be able to gain confidence while you face your original interview. And then previous company interview questions and preparation. So that is what, like previous companies, what questions they had asked, what kind of application oriented interview questions they have asked. Okay, previous batches, what kind of application oriented interview questions they have asked. So such kind of things also we will just train you with the interview preparations. Okay, we will just give you, like we will train you with what are the application oriented interview questions was asked in the previous batches. We will train you along with the answers so that you will be able to understand like what kind of questions are asked in the interviews, and if in case you get similar kind of interviews, how you can tackle them. So you'll be able to get an idea. So we'll be doing the previous interview questions and preparations we will be doing. Okay. And yeah, that's it for the demo. So if in case you have any questions, you can ask. So regarding the schedule and those things, like it will be informed to you from the admin team. So you'll be added into a DFT group, as well as you'll also be added into an individual group as well. Okay. So they will be posting the schedule in your DFT group. So from admin team side, they will be scheduling, or they will be posting the schedule for each week. They will be posting the schedule in that group. Okay. So schedule and timing, it will be posted by the admin team. They will be posting it into your WhatsApp groups. Okay. So if you have any questions related to the course, you can ask. Okay, so if there are no questions, then we can end the session. So yeah, thank you all. We will end the class. If in case you get any doubts in
Hello.
future,
Hi.
yes, you can tell.
Hi. This is Amir. So I work in one MNC company. So
Okay.
I work in embedded as a software engineer. I work. So
Okay.
I want to switch my domain, like from software to VLSI. So I am
Yes.
planning to switch to DFT.
Yes.
Is it possible?
Yes. It would be possible. So you can also once get it confirmed with the Webhauser as well. So he's the manager. So I'll just
Yeah.
share with you his number. So you
Yeah, I
can once
checked
get it
with one
confirmed.
Srikanth. I talked
Okay.
with Srikanth. So
Yeah.
he is the person. He suggests me, yeah, you can join the classes. You can able to change the domain if you want.
Yes.
But
Yes.
but
So I
what
have
what
seen some. Hmm.
what I'm thinking like I have a 2 year of experience in the embedded software, right? But as an
Okay.
associate engineer.
Okay.
If I did the course and I'll do some project, can I mention this as a 2 year experience in VLSI?
Uh, this particular course can give you like around 0 to 2 year experience. Yes, the project work which is given in the course can give you an
Uh-huh.
experience of around 0 to 2 years. So
Okay.
yes, you can mention it.
Yeah. That's the thing I want to know. That's why.
Yes.
What is the
Okay.
duration of the course? If I'll
So
join in May, when it will
yeah.
close?
So the total course duration will be like uh, 5 to 6 months. So let me
Okay.
just uh, write it here. So total course duration will be 5 to 6 months.
Okay.
So the first 2 months,
Mm-hmm.
2 or 2.5 months,
Mm-hmm.
they will be covering like basic
Okay.
GBIM. GBIM is a text editor, and then digital design, and then Verilog, CMOS, Linux, Pickle. So these basics they will be covering it for the first 2 to 2.5 months.
Okay.
And then the next 3.5 months to 4 months. So we will be covering the DFT advanced concepts. So which I presented in the uh, slide. So those topics will be covering into the next 3.5 months to 4 months.
So what I'm saying, I'm coming from the computer science background, okay?
Yes.
So my electronics is not that much good. So
Yes.
is it
So they will be covering those concepts like digital design. So when you do the
Mhm.
digital design part, so we'll be covering
Mhm.
everything from basic gates, from logic gates, combinational logic,
Ah,
sequential logic, all the topics will be covered in the digital
okay.
design part of the training.
Mhm. In
So
the
you will be
very
able
log, what I'm saying, in the very log, uh, we need to write in DFT. DFT is like testing, right? ATPG. My some friends are working in VLSI. Okay, they are saying
to,
that we are just running the things and generating the pattern. These all the work.
yes. So
Uh,
in Verilog for DFT engineers,
uh,
we will be covering some basics of Verilog, like what is a
okay.
module, and then how to basic like what is behavioral data flow level and gate level modeling. And then if in
Okay.
case you want to add up any mux or you want to change any connection, so how you can
Mhm.
do that. Okay. So such kind of basics will be covered in the Verilog part. For DFT, Verilog will
Okay.
be covered not much in depth, like overview will be covered.
Okay. Okay. Thank you. What? Thank you. That's
Yeah.
the thing I need to understand.
Yeah. Okay.
Okay. Thank you.
Yeah. Thank you. So, anybody else? Do you have any other questions?
Hello.
Yes, Shakti.
Hello.
Yes,
Yes.
Shakti.
Actually, I already enrolled for this course, but I am not sure why they asked to join in this demo section. I thought this is a live training section like that. I thought.
Oh, okay, I'm not sure about that. Can you check with the
Hmm.
admin team? They will be able to tell.
With Vibe,
No, not
whom I
right now.
need to ask.
There will be another sir over there. Um, do you
Hmm.
have an individual group created with the
Yeah. Yes.
individual group?
Yes, I have.
Uh, yeah, can you just message in that group? So from admin team, like they will be able to guide you. Like Suresh sir and Bharat sir, they will be posting the schedule. So like if you
Okay.
just message in that group regarding this query, so they will
Hmm.
be able to guide you on that.
Yeah. Okay. Yeah.
And what is the timing if I enroll in this course? What is the timing?
The timing will actually differ from one batch to the other batch. So, like
Okay.
the admin team will only be scheduling the batches and
So,
timings.
one day, how many hour I need to spend in the lab?
Even that it actually differs from one batch to the other batch. I'll just give you the number of give you admin's number, so you can
Yes.
contact sir. So they will be able to tell you like how your batches would be scheduled because
So,
the timing
what I'm saying,
durations.
no, no, what I'm saying, because now I am not in Bangalore. Okay, I'm in my hometown. I
Okay.
came for my festival. One of my festival is coming, so I came for my festival. I will be on the Bangalore, in Bangalore, 25 or 28.
Okay.
Yeah. So how I can manage my classes if I enroll in this batch, or I will enroll in another branch, or it will come next month.
You can even attend it like online or else like
Okay.
you can watch the e-learning videos. So
Mm-hmm.
after the session, they'll be giving you the session recording so you can watch the e-learning videos or you can
Mm-hmm.
attend few sessions online till you come to
Mm-hmm.
Bangalore, you can attend it online.
Okay. 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 Fine. Please share me the number.
Yes, one second.
Uh, what is the number?
One second, I'm typing in the chat box.
Yeah, you can type.
Yes, I've shared it in the chat box.
Thank you.
Okay, so yeah, if in case you have any further questions, you can like post it in your individual group. So we will be answering your questions in your individual group regarding the codes or any timings if you have. You can message in your individual group, or I've also shared with you admin's number, so you can like contact them, so they will be able to guide you. So yeah, thank you all. We'll end today's class.